Okay, we're going to do a lab today. Well, this is a lab you should be doing in class, but anyhow, we are going to investigate the relationship between voltage, current, and resistance, and we are going to use this little thing is called a resistor. That is an example of a resistor. Okay, the metal wire on either side is just metal wire to connect, and the resistor is this brown thing with the little color bands in the middle. We can have, I mean, there's all sorts of different types of resistors, so you can't really see that, but here's one, oopsies. Here's a one that's blue. This is the one I'm going to actually use. The little color bands represent the value of the resistance. I just wanted to show you something. This is from an old VCR, and you can see there are zillions of little tiny resistors. They're little tiny things. They're all over the place. Not the blue things, the little tiny resistors. You see them right here. They're all over the place. My point there is that electronics have lots of these things, these resistors. And the sole purpose of a resistor is to provide resistance. So we're going to investigate voltage, potential difference, voltage versus electrical current going through a resistor. And so given that the resistance, is constant, and that's one of our assumptions, by the way, that the resistance is constant, what is the relationship between voltage and current? Again, this will allow us to derive Ohm's law. Ohm's law is OHM. That's his name, George Ohm. So Ohm's law, which is the relationship between voltage, current, and resistance in specific types of circuits. Okay, so you should write down this data table. This is the EMF. Uses a funky little squiggly epsilon. It's measured in volts. And the EMF is the ideal voltage that you get out of the battery. So if you go, when you load up your calculator with those little AAA batteries, each of those is 1.5 volts. All right, but what may surprise you, and we'll have to talk about this another time, is that when you actually use your battery, you get less than 1.5 volts out of it, because voltage is related to energy. And you notice that batteries get a little warm when you use them. So some of that 1.5 volts in your 1.5 volt battery gets dissipated in the form of heat inside the battery. And so you actually, when you turn something on and have an electrical current passing through it, things warm up. So you don't get quite as much energy out of it as you do when it's not as it says on the battery. So EMF is the ideal value printed like on the battery. We're going to use 0, which is when everything's turned off. 1.5 volts, and if we had 2 batteries, we'd have 3 volts. 3 batteries, 1, 2, 3 batteries, but 4.5 volts, and then 6 volts, right? So that's going to be the ideal, but we're going to actually measure the voltage, which results, again, the voltage is related to energy, the voltage, the energy used up over the resistor versus how much current goes through the resistor. All right, so a typical meter looks something like this. We're not going to use one of these. These are the old analog meters for measuring current and voltage. Instead, I'm going to use stuff with from vernier. I'm going to use to measure the current. This is going to substitute for an ammeter, all right, to measure the current in amps. This will substitute for the voltmeter, okay, to see if there's any energy usage before and after the resistor. All right, it just compares the before and after, and if there's a difference, it's going to show up a potential difference in energy on either side of the resistor. Okay, instead of using batteries, I got tired of dumping batteries in landfills, so I bought this, which is called the battery eliminator. It just substitutes for the battery. When it's off, zero power, and so that's going to be the very first data point, 0, 0. And then I have 1 point on the selector switch. This is like 1 battery at 1.5 volts. Here's 2 batteries, 3 volts, 4.5, and is 3 batteries, and then 6. Okay, that's going to be, that's these. So I need to, this goes actually fairly quickly. I need to set this up. I'm going to use this little resistor. The fact that it's blue doesn't have anything to do with anything. The little color bands that are on here represent the value of the resistor, but we'll be able to figure that out actually from the experiment. So this is a circuit diagram, and the circuit diagram, this represents the battery, okay, the power supply, the battery. And the long line is the positive terminal of the battery. This is the symbol that represents the battery. The short line represents, the short line right here represents the negative terminal of the battery. And let's go ahead and set this thing up. So I am going to connect. Oh, before I show you that, let me show you something here. The readouts are gonna be on Logger Pro, but you're not gonna be able to see it. And I know you can't really see this very well, but I'm just gonna be reading, this is the voltage, and that's gonna be the current readout, okay? That's where I'm gonna get my numbers from, all right? Because all this stuff is plugged into a Lab Pro, and I'm going to get my readings there. All right, so the first thing I'm going to do is plug into the power supply and then into the current probe that the ammeter measures the current. So this is called just so you know, it's called a banana plug. And this is called an alligator clip, which is appropriate for Xavier gators. Yeah. Okay, so I'm going to plug that in here to the red. By the way, polarity matters. You go positive to positive. So I want positive terminal of the battery to the positive side of the ammeter. Now current passes through the ammeter, so I'm going to come out of the ammeter on the other side and go to the resistor. I know you can't see this very well, but that's, you know, whatever. Okay. This is a fail. Come on. It's not getting a good grip. Plus, I can't see very well. Sorry. Thank you for your patience. Okay. So that took a long time. So I connected from the battery to the positive red side of the ammeter, the current probe, coming out the other side, the black side, and I just clipped on, took me forever, to this side of the resistor. That's the symbol for the resistor. I'm going to come out of the other side of the resistor. All right, so I just clipped on right there, and I'm going to connect it to the negative terminal of the battery, which is right in here, okay? Then the last thing I'm going to do is connect the voltmeter. And voltmeters, remember, they just measure to see if there's any energy usage between here and here. If there was no energy usage, this would read 0 because that would be at the same energy level as that, the same potential. If we're measuring this as a potential difference, if there's any difference between this point and here, then energy either got used up or got added to. In this case, of course, it's going to use up the energy. So there will be a difference between these 2 points once I turn it on. So I put the positive terminal on this side, and I put the negative terminal, in polarity matters, on this side, and this is going to measure to see if there's any potential difference. So positive terminal, I know this looks a little weird. When you're drawing your apparatus for the lab, just draw that. All right, you do not have to draw this. This is just a mess. And let me tell you what I just remind you what I have here. Okay, so I have this whole thing connected now. Okay, that looks good. So I have a power supply, substitutes for the battery. I've got just a bunch of wires. This is the equipment. I've got a current probe that measures amps, current. I've got a voltage probe that measures, acts like a voltmeter, measures volts. And I've got a resistor. And so we're going to start collecting data. And our first data point is very simple. When the thing is not on, you have 0 volts and 0 amps. Whoops, this just went off on me. Okay, now I'm going to this goes very quickly. I'm going to, let's turn it on. And so you can see a little green light came on. And suddenly I have nothing. Oh, there we go. I have 1.498 volts, 1.498 volts being measured over the resistor from one side to the other. So it's using up a little bit of, it's using up 1.498 volts of potential. And the current is 0.0074. 0.0074 amps. 0.0074 amps. Let me up this to 3 volts, the selector switch, and that says 2.978. So the voltage reading, 2.978 volts. That's going to be plotted on the x-axis of your graph. Versus the corresponding current of 0.0151. 0.0151. Let's go to the next one, which is 4.5 volts. Let me get a darker pen. Who knows? So when I select 4.5 volts on the selector switch, that's like having 3 batteries. I am getting 4.460. 4.4. Ooh, that's interesting. 4.460. And the corresponding current going through the resistor is 0.0227. 0.0227. And lastly, because I'm running out of time here, when I go up to 6 volts, so I just changed the selector switch to 6 volts. That would be like having 4 batteries in your calculator. I get 5.940. 5.940 for the voltage. That's what this is reading. The selector switch is at 6. This is reading a 5.940 voltage usage over the resistor. And the corresponding current is 0.030. 0.0300. Okay, so those are my readings. So 0, 0 for the first one, 1.498 for the voltage, 0.0074 for the current. At 3, the selector switch is at 3. I get 2.978 for the voltage and 0.0151 for the current. When I'm on 4.5, I got 4.460 for the voltage, and then 0.0227 right here for the current. And then at 6 volts, I get 5.940 for the voltage and 0.0300 for the current. You're going to plot these on a graph using LoggerPro, 1 per lab group, and you'll have current on the y-axis. These are your y values versus the voltage. That's the middle column. The voltage used up over the resistor on the x-axis. All right, I'm going to run out of time, so I have to stop this.